Hello everyone, this is Sir Aris. Let us talk today about the divergence and the divergence theorem. We have defined the divergence of a vector function v as this del dot v equals partial respect to x of vx component plus partial respect to y of vy component plus partial respect to z of vz component. Now let us consider a region in which water is flowing. Suppose you have here a cylindrical region. So here there is a uniform area A prime. Okay, this is A prime. Just to be more clear here. So this is A prime. And water is flowing along this direction with a velocity v. And suppose at some point here, let's consider an area A or area A where water is still flowing to the right, but this area A is directed such that the normal unit vector n perpendicular to A makes an angle theta with V. For this region here, this the total length covered as the water moving from this position to this position would become the magnitude of speed or velocity, which is the speed v, times the total time it takes for water to flow from this position to this position. So that's vt. Okay. We assign at every point a vector v equal to the velocity of the water at that point. And the curves tangent to v are called streamlines. Let us set capital letter V equal to velocity v times rho, where rho is the density of water. So the amount of water crossing in time t, an area A prime, which is perpendicular to the direction of the flow, is, so the volume is V Vt times the area. So that is the volume. So volume times density, that would give you the amount of water in terms of its mass. So let's use multiply it by density. So V, small letter v, times rho, that gives us the magnitude of V. So we can write it as V T A prime. At A, over here, we have the same amount of water crossing the area A, but the expression in terms of area A would be different. So we have VT A prime rho initially, but in terms of A, it becomes VT A rho cosine theta because of this theta here. So we project our V on this direction, the direction of n. So we multiply V by cosine theta. Or you can project this area normal to the area towards V. So in both cases, we either or we either use both the two cases. So in both we multiply by cosine theta. So this we can write as V times rho is capital letter V T A cosine theta. If water is flowing in the direction V, make an angle theta with the normal n, the amount of water crossing unit area A. So this A, suppose that is equal to 1, and time is also 1. Then we have V, the water flowing would be V cosine theta. Okay, this is for V making an angle theta with the normal end. So that corresponds to this region here. Or this we can write as V dot N. Okay, so remember that this is the amount of water crossing. We divide it by T. So for example, this if you use this, we divide this by T. That would be the rate of water flowing. So that would be, so if you divide this by T, T cancels, so we have VA cosine theta. That's the rate of water flowing. We divide it by A, so we are left with V cosine theta. That would be the rate of water flow per area. So this is the rate of water flow per area. Now let us consider an element volume dx dy dz in the region through which water is flowing. Let's consider this coordinate system. This is the x-axis, y-axis, and z-axis. And suppose this volume element is a box whose sides are, whose one corner is at the origin and the other sides are, let me draw this properly. So this is, okay, our volume element. This has length dx, this is dz, this is height dy. So the volume is dx times dy times dz. Suppose on this left side, let's call that surface area 1. On the right side, let's call that surface area 2. So the rate at which water flows through surface 1, that would be V dot I, because I is the unit vector along x. So this is the rate of water flow per, this is per area. So we are looking for water flow on the specific area. So we multiply this with the area. The area is dz times dy, so, or dy times dz. What is V dot I? So V dot I is Vx. That's the x component, dy dz. So this is at surface 1. Okay. At surface 2, you have V dot I dy dz, but this time you evaluate this, okay, at surface 2. Basically, so dy dz is still the same, but this is at surface 2. So we have V x at surface 2 dy dz, which we can write as same Vx here at surface 1 plus a delta Vx, okay, times dy dz. Basically, we're adding an, if here there's Vx is the x component here, let's say Vx plus delta Vx. So the net outflow through this two surfaces is the outflow through surface 2. So surface 2 is this. So we have Vx at surface 2 minus Vx at surface 1, okay, dy dz. So surface 2 is this minus this. So you have Vx plus delta Vx minus Vx, that's delta. So this is delta Vx dy dz, which is approximately dvx dy dz. For constant y and z, we can write dvx as partial derivative of vx with respect to x dx. So we have here, this is equal to partial vx with respect to x dx dy dz. And we get similar expressions for the net outflow through the other two pairs of opposite surfaces. So through top and bottom, you have partial derivative of vy with respect to y dx dy dz. So through so top and bottom is this, and this. So we still have this front and back. So through front and back, you have partial derivative of v with respect to z, vz with respect to z dx dy dz. It's along this z direction. Okay, so the total net rate of loss of water from dx dy dz would be, so we just add this plus this plus this. So that would be partial vx with respect to x plus partial vy with respect to y plus partial vz with respect to z dx dy dz, which is just the divergence. So if we divide this equation by dx dy dz, we get, so we divide this by the volume, it would be the rate loss of water per volume. And that would be then the divergence is the rate of outflow per unit volume evaluated at a certain point. Let psi equal to the source density minus the sink density. Basically, if we have a source, something, if we add something on our system, but there's also a sink where something is being removed, the net addition would be given by psi. So that's the net mass of fluid being created per unit time per unit volume. Rho is the density of the fluid, so it's mass per volume. Partial rho with respect to t is the time rate of increase of mass per unit volume. Mass per unit volume is the density. So the rate of increase of mass in dx dy dz, so that's this partial rho partial t, so increase of mass. So this is mass per unit volume. Volume is dx dy dz. So we include this dx dy dz. So the rate of creation is the rate of psi, so or psi. So you have psi dx dy dz, okay, minus del dot v, which is our rate of outward flow, dx dy dz. Okay, so to be clear here, this psi is our rate of creation. Okay, so if you have, if we divide, so we cancel dx dy and dz, you have partial rho with respect to t equals psi minus del dot v, or del dot v equals psi minus partial rho with respect to t. So if there are no sources or sinks, then psi equals 0. If psi is 0, then you have del dot v plus partial rho with respect to t. If you move this to the other side, this is equal to 0. And this is called the equation of continuity. Also, if partial rho with respect to t equals 0, then if there's psi is non-zero, then del dot v, so this is v, equals psi. Okay. Consider any closed surface and let d sigma represent an area element on the surface. For example, for a plane, d sigma is dx dy. For a spherical surface, it's r squared sine theta d phi. Let n be, or the unit vector n be the vector normal to d sigma and pointing out of the surface. The mass of the fluid flowing out through d sigma is v dot n, which we know. So which we have derived earlier. So the total outflow from the volume enclosed by the surface is just this double integral. This double integral is evaluated over the closed surface. Alternatively, we have shown that for the volume element, the outflow from d tau is del dot v d tau. So these two should be equal, where this is overall the closed surface enclosing d tau. So we divide both sides by d tau and get the limit as d tau approaching 0. We have the definition for del dot v. Consider a large volume tau cut up into volume elements d tau. So suppose this is our tau. Okay, total volume is tau. We cut this up into small volume elements. And suppose, let's call this one d tau 1. This is d tau 2, d tau 3, and so on. Okay. So the outflow for each d tau I is del dot v d tau I. And we add all of them so that we get the net outflow, so it's just the sum of this. But let's say, if you consider one region here, so one element here, the outflow would become the inflow of the other. So the outflow, if there's a net outflow, or say there's also an inflow, but that would cancel out with the inflow or outflow of the adjacent element. So they would just cancel. What would not cancel would be the outflow on the sides. So the outflow across interior faces cancels, so total is just the outflow from the large volume. And as the size of the volume elements tend to 0, this sum approaches, so the sum here approaches a triple integral over the volume. So, and that's the total outflow from the large volume. We have shown earlier that the total outflow from an enclosed volume can also be written as this. So these two should be the same. We have the divergence theorem. Note that the divergence theorem converts a volume integral, in this case, this left-hand side, into a closed integral over a closed surface, this. Or if you have an integral over the closed surface, you can convert that to a volume integral. It's common to write only one integral sign instead of writing two or three integral signs. For example, if you have a single differential, let's say d tau, dv denoting volume element, d sigma, dA, ds denoting area element. So the interpretation of our single integral would depend on what type of element we are uh, considering. So this triple integral d tau would mean the same as this d tau or dx dy dz triple integral. For surface integral over a closed surface or a line around a closed curve, we use the symbol integral with a circle. For a surface integral over a closed surface, we may either write so this over all surface or this integral with a circle. Also, we may write the sigma vector, meaning it's a vector of magnitude d sigma, but in direction of n, where n is a unit vector directed towards a perpendicular or normal to the surface element here. So we may replace v dot n d sigma by v dot d sigma, or n d sigma would mean the same as the sigma vector. Let's consider an example. Evaluate let v given by x, y, z. Components are x, y, z along x, y, and z directions respectively. Evaluate this over the closed surface of the cylinder shown in the figure. So suppose this is our cylinder. Oops. And the cylinder has radius a and height h, and it is positioned such that the bottom center is at the origin. So let's call this our y axis over here. This is our suppose x axis, and this is our z axis. Oops. Okay, the radius is again a. So using divergence theorem, you have closed integral of v dot n d sigma equals del dot v d tau, where the integration is overall volume of cylinder. Okay, so for del dot, if you use this expression, del dot v is simply partial with respect to x of vx plus partial with respect to y of vy plus partial with respect to z vz. Vx, vy, vz are, you have x, y, z. So you have partial x with respect to x plus partial y with respect to y plus partial z with respect to z, which is simply partial x with respect to x is 1, partial y with respect to y is 1, partial z with respect to z is 1. This is 3. So if you continue here, close integral of v dot n becomes integral of 3 times d tau. This is volume of cylinder. So basically the answer would be 3. So this is 3 d tau, where this is just the volume of the cylinder. Okay, so this is 3. The volume of cylinder would be this area times this height. The area would be pi a squared. It's pi a squared. Height is h, and that would then be our closed integral over the cylinder. Okay, it's quite easy when we converted to a volume integral.